Hello, my name is Don Metzger. In this video, we will be showing you how to set up and run an Analog Devices AD9084 Apollo chip on an eval board that's being hosted by a Xilinx VCU118 host board, running under Analog Devices IIO software and using Quick Transceiver by Quick Systems. First, we'll be showing you the board setup, and then how to bring up the VCU118 board, and then how to confirm that the correct configuration is running. We'll then bring up Quick Transceiver and show you how to set that up, and then we'll run a 64 QAM transmit-receive signal, and we'll show you an improvement using adaptive equalization and then some amplification. So the first thing that we want to do is to plug in the power for the 9084 eval board. Then we plug in the power for the VCU118 board. I turn the power switch on for the VCU118 first, and then I turn the power switch on for the 9084 eval board. Here are the steps that we'll be going through to get the system programmed and up and running, but we're going to walk through this together. On a PC that's connected to the USB UART and the USB JTAG ports on the VCU118, I want to bring up a PuTTY terminal for the serial connection that's the USB serial connection. Just have that open and up. And then I want to start up the Vivado TCL shell. And on the TCL shell, let's navigate to the folder that has the boot TCL file in it. So you want to do dir to find out the contents and the location of where you're at. So let's change directory to D AD9084, do a dir again, change directory to the VCU118 underscore QIQ directory, do a dir again, and there we have our boot VCU118.tcl file. In the TCL shell window, we want to type XSDB, and then we want to type source boot underscore VCU118.tcl, and it should begin the process of loading the firmware image onto the VCU118 board. This is going to take a while. It will tell you how much time it has left in the process as it does the boot. As soon as this process is done, it switches over to a boot of the system. Okay, we're almost at the end of the loading process. The next thing that's going to happen is to boot the CPU, so let's switch windows over here to our PuTTY terminal window and see the boot process. Okay, we're coming to the end of the boot process now, and it's going to ask me for a login. I'm going to do root, and I'm going to do analog, all lowercase. And there we are. So the first thing I want to do is just check the IP address. So I'm going to do ifconfig and make sure that I know what the IP address is. It's 35 in this case. So one of the things that I like to do at this point to just verify that the system has been loaded correctly and is running correctly is I do an IIO underscore info and have it tell me all the IIO devices that it found. And I can tell already that this has been successful. It's going to go on for quite a while and list for us all of the IIO things that it found as it was setting up the system. All right, now that the system's up and running, I'm going to switch computers to another computer on the network, which will talk across the network to the VCU118 board. Let's make sure that we have the right connections. I'm going to be using the program Quick Transceiver. We are talking to a 9084, which is hosted by a VCU118 over the network at that IP address. We're going to be going to the 9084 settings. We're going to talk out DAC A0 with a loopback cable. It's at 2 gigahertz. The receive channel will be ADC A0 at 2 gigahertz, and we'll be acquiring 40,000 samples. For transmit waveform, I'm going to be using a 64 QAM signal with 500 megasymbols a second, and it is 2.5 gigasample per second sample rate. And for Windows, so we can see what's going on, acquired waveform, acquired spectrum, acquired spectrogram. We'll look at the constellation after the demod. Adaptive EQ response we'll look at a little bit later, and the measured results. All right, let's start it up and running. There we go. We are transmitting and receiving a 64 QAM signal at a symbol rate of 500 megasymbols per second. That's about an occupied bandwidth of around 500 megahertz. And currently with this 64 QAM signal, we're seeing an EVM of about minus 28 dB or 3.8%, something like that. Okay, if I stop the playing so that we can look in a little bit more detail, you can see that across the top of the spectrum of the signal, there's a little bit of ripple that's in there. There's a lot of RF stuff in the system. There's the chip itself, there are balance, there are launches, and so we have a little bit of non-flatness in the system. And in our software, you can correct for that with some adaptive equalization. So let's go in here and turn on some adaptive equalization, and we'll give it 33 complex taps to use in trying to clean up the signal. And let's run it again. And yeah, that's a lot better than it was. Up here in the top right now, you can see the adaptive equalization that is being applied to the received signal in order to make the final constellation better. Let's stop it again. The DACs on the AD9084 put out somewhat less power than other members of the family like the 9081 or the 9082. So we like to use an amplifier to bring up the output of the DACs for the sake of the ADCs. So let's stop this. We'll go in here and we will turn off the adaptive equalization for the moment, and we'll just use an amplified signal coming from the DAC output running through an Analog Devices AD9100 amplifier, and you can immediately see that the signal level is better in this case. EVM still around 3% because we still have the ripple issues because we've turned off that adaptive equalization, but the signal to noise ratio is looking much better. So now if we go in here and we turn on our adaptive equalization, you can see how much better the final constellation is. We're getting now EVM close to 50 dB down, about 0.3% or so, and you can see what the adaptive equalization is doing here to compensate for the ripple across the band, Ripple's a little bit different because we have this amplifier in here now. It's added to it. So the ripple compensation should not be exactly the same as it was previously. But anyway, this is a pretty good constellation, 50 dB down over a 500 megahertz usable band. That's a good tight constellation. All right, the last thing I'm going to do for this video is to find out the effect of adaptive equalization, the number of taps we're using. So let's start the system running. Here's it's running 33 taps in there. I'm going to just go up to 65 taps in the adaptive equalization and see the effect that that has. And you can see that improved our EVM a bit. We're getting very close to the carrier to noise ratio with this. It did make the out-of-band response for the adaptive equalizer a little bit better. And you can see that's just really an excellent final symbol constellation over a 500 megahertz bandwidth. Okay, that's it for the measurements. To learn more about the Quick Transceiver software, you can visit us on our website at quicksystems.com, or you can contact us by sending an email to sales@quicksystems.com.